Today we think of like this, just observe. We learn about how to measure the pressure inside a fluid. In fact, we take liquid only. It's easy to understand. Say like this. This is the liquid boundary. And also, this is the liquid boundary. We imagine, just like yesterday, what we did, a small portion of the water or liquid. It's not nothing immersed there. It's a small cylinder, cylindrical part of the liquid itself. That is water if you take. Now we write the pressure at this point. Say force is acting down on this, and on this it's acting up like this. And force acts on sides also like this. On this part, it's not nothing immersed there. It is simply a portion, just like what we said yesterday. Now, observe, we take this as 2 and this as 1 for the sake of reference. Then we write, say, force at 2, force at 1, and all other ideas. Whole of this is at rest. That means net force acting on this cylindrical part is 0. And we take the height of the cylinder as h. So what is the net force acting on it? Say I write the F2, the upward force, minus F1, the downward force from top, and then minus mg equals 0. Net force should be 0. Therefore, F2 minus F1 minus mg is 0. Because why minus 1, minus sign is there with F1 and mg? They are downward. F2 is upward. Now observe, we write down all the things. F2, in terms of pressure, if I write, P2 into A. Because we know F by A is pressure P. So P2 into A minus P1 into A, where area is area of this part or this part. We take this mg onto this side. Very simple thing. Say we take P1 A as common factor. And I write mg, m, in terms of mass and say volume and density. What is that? Can you tell me? How to write mass in terms of volume and density? Mass by volume is density. Mass by volume is density. Therefore, mass is rho into volume. Rho is density. Volume is V, G. And observe, we know volume of this can be written as area A of this or this right circular cylinder is there into H, the height. You write usually pi r square H in the geometry, pi r square H in the geometry, but we write instead of pi r square, we write A as the area. Now substitute everything, P2 minus P1, A equals rho A G H. I write G first. Cancel A there. P2 minus P1 is rho GH. In fact, P2 minus P1 is rho GH. In fact, this is what we call as gauge pressure. But observe, we think of slightly different idea, but this is the pressure difference between top and bottom and top. But if we imagine now, this top surface is exactly on the top of this surface of the liquid. This one is on surface of liquid. Here the pressure is acting by the atmosphere. We call it as P naught or PA. We call it PA. PA is atmosphere pressure. And in that case, the depth is H. I can write it as P minus PA. P2 I call as P. P minus PA is rho GH. P minus PA is rho GH. In fact, this is what we call as gauge pressure. Gauge pressure. That is what you measure. Gauge means to measure. What you can gauge. Gauge pressure is P minus PA. What is the true pressure then? It is measurable. What is the true pressure? PA plus rho G H. PA plus rho G H. Gauge pressure is PA plus, say, P minus PA rho G H. Actual pressure at depth H is PA, the atmospheric pressure, plus rho GH, the density of the liquid, acceleration due to gravity, and height H. This is the formula for true pressure at any point inside the fluid. And this is the formula what we call as gauge pressure. Gauge pressure means how to define. You may be asked to define gauge pressure. How to define? It is the difference between the actual pressure and the atmosphere pressure. Actual pressure and the atmosphere pressure is what we call as gauge pressure, what we can measure actually. And then P equals PA plus rho GH is the final answer for true pressure. This derivation may be asked for 5 marks or 3 marks. So write down the question. Later on, I'll just go through it once again. Write down the question. Derive an expression for pressure exerted by the fluid, at depth h, What you are supposed to write for this, just I will tell you now. Think like this. How much you are supposed to write, I will just tell you. Say a very simple idea. First, write this figure and write a word sentence, 1 or 2 sentences. Consider a liquid at rest or fluid at rest as shown. Then consider a small cylindrical portion of the fluid as shown. That's it. Once you write that cylindrical portion, height is h, and area of cross section of circular faces is a. That you write down those 3 sentences. Then the bottom portion 2, that is face 2, is acted upwards by force F2, and upward topmost say face, circular face acted PA, that is from the top is the force F1, and weight of the thing, what I have not written, weight of this cylinder acting down, mg, from the center of mass. So with this, we apply the Newton's second law, that is force equation what we learned in chapter 5, laws of motion, F2 upward, 2 more, F1 and mg downward, that's applied with minus sign is equal to 0. Or else you can change it direct. Then F2 can be written as from this formula, pressure into area. At 2, P2 is the pressure, area A. At 1, P1 is the pressure into area, which is equal to mg. But m can be written as density into volume, I have written. But volume is A into H. So P2 minus P1, like this, rho GH. This is the formula. P minus PA is called as gauge pressure. And then P equals PA plus rho GH is actually called as true pressure. Okay. This derivation, just go through it quickly, write down. Write down this quickly. Within 1 or 2 minutes, you can do it. Write the figure and then write. Now we proceed on to next thing. Just observe. In this expression, P equals PA plus rho GH, nowhere area of the cylindrical part comes into picture. That means pressure is independent of the area there because it is force per unit area, as this name suggests. Just write down a small problem there and then we go for the other thing. What is the pressure on swimmer? What is the pressure on swimmer? What is the pressure on swimmer? 10 meter below, 10 meter below the surface of lake. 10 meter below the surface of lake. How to calculate this? Say we take like this. What are the things given? 10 meter, that is the height or depth in fact. And density of the sea water or water you can take 1000 kg per meter cube. G we can take 10 for the sake of simplicity. And then only that much is required. Atmosphere pressure you can take, that we learn slightly later. 1.013 into 10 raised to 5 Newton per meter square. This is the formula for atmosphere pressure. So with this, you go for calculation of the pressure. Pressure formula is this one. P equals PA plus rho GH. Substitute everything, you'll get the answer. Do it quickly. Substitute everything. P equals PA 1.01 10 raised to 5 plus rho 1000. What we can write as 10 raised to 3. Number wise 10 raised to 3. G 10. H 10. So how much it is? 1.01 10 raised to 5 plus 10 raised to 5. So take out 10 raised to 5 common factor. That is 2.01 10 raised to 5 Pascal or Newton per meter square. Or approximately you can take 2 atmospheres. That tells you, in fact, if you just go down by 10 meters under the water, around 33 feet approximately, the pressure on us is doubled compared to what on us above the surface of water. So that is why it is very hard to get into the deepest parts of the ocean, even today. It is very hard because pressure just 100% increased when we go down by 10 meters, around 33 feet. There, thousands of feet down are the, say, depth of the ocean. Then if you go there, you can think of how much pressure is there on us. Therefore, the idea is this example tells us how the pressure increases inside the liquid, especially in water. So with these things now, we think of one more idea now. Once you learn gauge pressure and all those things, we think of one more idea, just also. Say long back in Italy, one person got some confusion, some doubts. He started doing some research. What is his experiment? I'll tell you. He took a very long tube, glass tube, something like test tube, like glass tube, around 1 meter length, very long tube, 1 meter length. Then he filled it completely with the mercury. He filled it completely with the mercury. And he temporarily closed the lid there, opening. Then what he did, he just took another trough where mercury is filled again. This is also mercury. And he inverted the tube inside it. After immersing the opening end, that is temporarily closed end, inside the mercury, he opened that. He opened that end. Now, say mercury is heavier. Its density is 13,600 kg per meter cube. Say around 13.6 times more than water. It is heavier, so much heavier. And can you think of what happened? in this experiment. With so much of heavier mercury, not all mercury came down out of the tube because so much heavier it should pour out when we inverted it inside the mercury. But it has not happened. What happened? To his astonishment, it stopped around 76 centimeter. Only this much came out and all other things remained intact inside the tube. And that showed something is balancing the weight of this mercury column. What is that? He investigated. There's something pushing this mercury outside downwards so that it supports the weight of this column of mercury. Weight of this column of mercury. Can you name that scientist who created this experiment for the first time? The Torricelli. Torricelli, the name of the scientist who did this experiment for the first time. And why this stands? Because the air outside, what we call as atmosphere, is pushing this mercury like this, so it can make this 76 centimeter column of mercury to stand. In fact, in chemistry, when you are doing calculations, you take standard temperature and pressure. In that pressure, you take 1.013 10 raised to 5 Pascal or 76 centimeters of mercury column. What does that 76 centimeter mercury column? This is the one. This is the one. That means this much of weight is balanced by atmosphere, what we have surrounding us. And this experiment of Torricelli proved to us atmosphere is there and it exerts pressure on us. Can you believe this atmosphere is keeping us intact? Otherwise, if it is not there, in a fraction of seconds we will be burst into pieces because inside us lot of pressure is there because of the blood and all those things. And once outer atmosphere is removed, we will burst into pieces, shattered into pieces. Why? Because of enormous pressure inside. That pressure is balanced by atmosphere pressure. Can you believe? Every one of you lift a weight. You're always a weight lifter, including me. We're all lifting around 480 kgs on our head every moment, every second. Can you believe? Can you calculate? Say, take like this. Our head is of order, approximately we calculate 10 centimeter length, 10 centimeter width, our head. 10 by 10. Then pressure is 1.01 10 raised to 5 Pascal. Multiply this by area, you will get the force, that is Newton. We'll calculate kg equivalent later on. Do it quickly. 1.01 10 raised to 5 into 100 centimeter means 10 raised to minus 4. We'll see how many kgs we lift. It may be slightly different. Okay, nothing to worry. So 100 into 1, approximately we take 100 into 10 raised to 1. 10 raised to minus 4 plus 1 is 1. 100 remained. I have not taken 0, 1 there. 100 into 10 raised to 1. What is it? How much it is? 1000 Newton. 1000 Newton force acts on our head if it is 10 centimeter by 10 centimeter. Then in kg, say F equals mg, you just apply. M equals F by M, F by G. If you take G as 10, it is 100 kg on our head. 10 centimeter by 10 centimeter if you take. 1000 by 10, which is 100 kg. That's why I said, every one of us are weightlifters. We lift every moment on our head. Just with an area of 10 by 10, I calculated on our skin, on our shoulders. It may be much larger. That's why we are good weightlifters, knowingly or unknowingly. So we are lifting around just over head of 10 by 10, it is 100 kg. On the shoulders, unlike that, it is much larger. So that is because of the Earth's atmosphere pressure. With this, observe what is here. The mercury came down up to this and stopped. What is here in the topmost part? Can somebody tell me what is there? Air cannot pass on there. It is completely vacuum. This is vacuum. It is vacuum. Prajwal, you are right. It is vacuum. Apart from small stray mercury vapors there, if at all, if they are. Vacuum. This vacuum is called as Torricellis vacuum. Torricellis vacuum. Zero pressure there. Zero pressure. And what is the pressure at this point? Can somebody tell me? What is the pressure at this point inside the tube? What I am marking now. What is the pressure at this point? Can somebody tell me? Think on it. At this point, what I marked with cross. You have not thought of or you have not applied what you learned. I will tell you. All of you, just observe carefully. Say this point. This point is at 76-meter depth inside the mercury. And it is supporting the weight. The pressure at this point is supporting the weight of that. As we said, it is lifted up. And I told already then, you could have thought of it, you have missed it most probably. Say, this is supported by outside force on this. That's what by atmosphere. That means, what is the pressure here? That is PA, what we have written in previous idea. Pressure of atmosphere. Here also pressure of atmosphere. And if pressure is more than atmosphere pressure here, then it would have flowed out. If it is less than here, this would have inflowed. Both of them are not happening. So no flow outside, no flow inside. That means the pressure remains same there. Observe how we are applying. The fluids flow from high pressure to low pressure. You all know. If that is the idea, when as soon as I ask you what is the pressure at this point, you must think like this. This is the thinking methodology, my dear friends. If the pressure is something different here at this level, then this mercury, either it has to flow if it is more here, it is less force, or it has to flow out like this. But if it is less here, the mercury from outside should flow and it should rise up. Both of them are not happening. That means to say, what is pressure outside? Here also pressure. So that is why we measure atmosphere pressure as 76 centimeters of mercury. Okay, with that. And this is called as Torricellis vacuum. And what is the unit of atmosphere pressure? Bar. Bar is the unit of atmosphere pressure. 1 bar. Bar is the unit of pressure. And also to honor the Torricelli, who for the first time showed us actually there is atmosphere pressure on us. To honor him, there is one more unit called tar. What is bar and what is tar? We want to learn. Bar is higher pressure unit. It's 10 raised to 5 Pascal, approximately 1 atmosphere. Tar is 1 millimeter of mercury. 1 millimeter of mercury. That means it is the pressure exerted at the depth of 1 millimeter inside the mercury. 1 millimeter, very, very small pressure. That's why it is called as 1 tar. 1 tar means 1 millimeter of mercury column pressure. Just now we said atmosphere is 76 centimeters of mercury column. And 1 tar is 1 millimeter. Just if it is the surface, Above that, you take 1 millimeter of mercury. What is the pressure at that 1 millimeter? Rho GH you can take. Then that is called as tar. Tar is the unit used to measure the low pressures. Okay, with these things. Once we learn tar, bar, and all those things, 760 tar, nice. 1 atmosphere can be written as 760 tar because 760 centimeters, 1 bar you have to calculate. 1 millimeter means 1 tar. 76 centimeters means 760 millimeters. So 760 tar. Okay, write down this small numerical. The density of the atmosphere. The density of the atmosphere at sea level. Density of the atmosphere at the sea level is 1.29 kg per meter cube. 1.29 kg per meter cube. Assume that it does not change. Assume that it does not change. How high the atmosphere extends? They are asking us how to calculate this. Just simple idea. Use rho GH. Use rho GH. P equals rho GH. What you take for P? 1.01, 10 raised to 5 Pascal. And rho given 1.29. G you take 10. Calculate H. Go for it quickly. You take this as 1 itself for the sake of easiness of the calculation. Just go for it. You'll get the final answer. How much you get? H. 7989 meters, approximately 8,000 meters or 8 kilometers. Up to 8 kilometers, we have air, atmosphere extending from the bottom surface of Earth. But here we made a crude assumption. The density of the air remains same at all points, but it is not like that, my dear friends. Even at the say top of the Mount Everest, it is very, very less density because as we go up and up above in the atmosphere, air density goes on decreasing because of the less and less particles like that. Okay, whatever it may be the thing, just take this. Then this thing, one application of or one method to measure the pressure. How? Just observe carefully. If you have written it, now we'll go. Proceed. You open YouTube manometer. Open YouTube manometer. That means you have to measure pressure of a device or from a point when you are doing an experiment. How we measure? That we do like this. Just observe carefully. It is like this. Say we have a gadget here whose the pressure to be measured here at this point inside this. For that, we have a device here. We have a YouTube, one side open to atmosphere, on the side it is connected to the device where we want to measure, and it is filled with a liquid. It's filled with a liquid. It's filled with a liquid. In fact, originally both the levels must be same if it is not connected. Here, there's the liquid. Originally, if you don't connect it here, they are one and the same. But if here the pressure is more than atmosphere pressure, then this pressure pushes the liquid, it rises up through a height h. Through a height h. If rho m is the density of the manometer liquid, this is called as manometer. Manometer, barometer. Barometer is used for measuring the atmosphere pressure. Manometer, YouTube manometer means it is used to measure the pressure of the gadgets what we want. Then just like tire pressure, pneumatic pressures in the petrol bunk what we fill for our say vehicle tires like that. Rho m is the manometer liquid. It's not shown, actually it's not seen in the Actually, petrol bunks, it's not like that. It's some other electronic idea there. But rho m. Now, what is the pressure here? We have to calculate. How to calculate that? Say here P is the pressure. Here is PA is the pressure. P minus PA is the gauge pressure now. At what depth H? So I must write rho m G H. M is manometer liquid density. What you use there? GH. This is the thing. If you want to measure low pressures, we use lighter or low density liquids here. If you want to measure high pressure, we use high density liquids like mercury. That depends on the situation. This is called as U-tube manometers, which helps us to measure the pressure. So with these basic ideas, now we proceed on to the next last bit. One more numerical is there. I just dictate if time permits. I dictate this numerical, write down. Only this manometer and all those things, you just learn. Write down the next numerical. At a depth of 1000 meter, at depth of 1000 meter, at depth of 1000 meter, in an ocean, part A, there are many parts, part A. What is the absolute pressure? Question mark. What is the absolute pressure? Absolute pressure means true pressure. Question mark. Part B. What is the gauge pressure? Question mark. What is the gauge pressure? Question mark. Part C. Find the force acting on the window of area 20 centimeter by 20 centimeter. 20 centimeter by 20 centimeter. If time limit exists and it will be over, I will not continue. No, we'll see. Mostly time limit illa ivattu. So we'll solve this. We'll finish off this. Find the third one, part C. Find the force acting on the windows of the area 20 centimeter by 20 centimeter. Just now how we calculated for area on our head 10 centimeter. In the same way. 20 centimeter by 20 centimeter of a submarine at this depth, the interior of which, that is interior of submarine, the interior of which is maintained at sea level, atmosphere pressure. Interior of sea level, say, is maintained at sea level, atmosphere pressure. Given the density of sea water, 1.03 10 raised to 3 kg per meter cube. 1.03, slightly larger than 1000, 30 kg larger, kg per meter cube. So 1003, 10 raised to 3 kg per meter cube. And G, the acceleration due to gravity, you can take 10 meter per second square. Can you do this on your own? Just do it quickly. Finish up this. Direct calculation. What is the absolute pressure? What I said as true pressure. P equals PA plus rho GH. Do it quickly. Gauge pressure is P minus PA. First calculation is this one, second calculation is this one. Or else the easy way is to do first, second calculation, gauge pressure. Later on add atmosphere pressure to that, you will get the thing. 104 atmospheres. 104, that's right. You will get first thing true pressure as 104 atmospheres. 104 atmospheres. 1 atmosphere means 1 into 10 raised to 5. You can take 1.01 10 raised to 5. Or else 5. Actually, actual answer what you get is 104 into 10 raised to 5 Pascal you will get. That is 104 atmospheres. 1 atmosphere is 1 into 10 raised to 5 we take. Then gauge pressure is 104 minus 103. Nice. The pressure inside the submarine is kept at PA, atmosphere pressure. It is given value there. So what is the value of the force exerted? How do you calculate? Force exerted on the windows. How do you calculate? What is the gauge pressure? That multiplied by area. Not only rho GH, gauge pressure rho GH into area to be done. That is 103 atmosphere into area 20 by 20 centimeter square. So you make it 10 raised to minus 4. Do it quickly. After doing this, we conclude this class. 4.1 to 10 raised to 5. Okay, nice. Force on the window is, you can calculate that as PA, gauge pressure into area, which will give you can do it on your own, 4.2 10 raised to 5 Newton. That is the answer. Just calculate gauge pressure 103 10 raised to 5 into area 20 into 20 10 raised to minus 4. 103 gauge pressure to be taken, not 104. Actual pressure, absolute pressure is 104. Gauge pressure, after subtracting the atmosphere pressure 1, you'll get 103. So that is 4.1 to 10 raised to 5 Pascal. So 5 Newton, in fact, force it is. So with these things now, we conclude this meeting.